Hello students, this is Dr. Diaz and I'm here today to reduce and to ensure the class that we had today. This week I call the carbocation week. Why I call the carbocation week? Carbocation week is because we had rearrangements. Yeah, the test two we moved to Monday for Dr. Diaz, me, and Tuesday for Dr. Broomfield. So after the break. Okay, so the only thing that changed for early is the video for Unit 3 will be moved early, October 8th, and reading the diagnosis will remain, but I recommend that you doing this week before the video. Then after the test, we return to our regular schedule. So short videos, please, all the questions that students send to me, I answer through videos. So because I received some equal questions and probably you have the same questions. So go there, it's easy to find because the title is exactly the question the student asked me. So I answer those questions. And also, you're gonna find the classwork 14 plus extra points available. So today I made a Kahoot with the students, so they have the opportunity to get extra credit. And then since I want everybody get the same opportunity, I send you an email with the link for the Kahoot. Please participate it. And the classwork that you're gonna find there is to complete the classwork 14 that you're gonna do Willie, and you're gonna see there the question number 6, and please read the email that I gave you instructions to that. Okay, so but I will answer the question since most of you didn't watch my videos. So the last question was, did the elimination reaction always favor ZF? If you ask me this question, as I said during class, elimination reactions will not always favor ZF. That's a general question. But if you ask me, E1 reactions will favor ZF. Yes, this is always favor ZF, generally favors ZF, which is more stable isomer. And remember how that works. So first the halide will leave and will take the electrons with it. And then and the E1 reaction, we know that we have a positive charge, right? And the positive charge is over here. So we have this alpha carbon, which is the carbon that carry out the halide and the negative charge, and we have the beta carbons. So the beta carbon is who's around. So we have this beta carbon over here, and we have a beta carbon over here, and we have a beta carbon over here, right? So we can have, if you attack this is a beta carbon, right? So what are you gonna have here is the attack of the nucleophile over here. So we'll attack, or the base, I'm sorry, can attack the hydrogen that you're gonna have over here. So we're gonna attack this, extract this proton over here, and we're gonna have this proton will leave behind a double bond. And but we also can attack this one over here, right? So and then we're gonna have this one over here. And this, as you can see here, is less substitute than the other, because here I have just one substitution, and here I have 1, 2, and 3. And if you have a 1, 2, and 3, we call tri-substituted. And the most substituted here is the ZF, right? And this is the Hoffman. Hoffman is not the major here. The major is site F. Okay? However, if you go to E2 reactions, E2 will depend, so will depend of the base. If you have a small base, we can have the major will be the site F, right? In this case over here, we have, again, so just one substitute here, while here have 1 and 2, so di substituted. But imagine if I have here, so bromine, and I have a buck base over here. So I'm gonna call, remember that I showed you butoxide, that it's a very good and strong base, but it's not good nucleophile because it's buck. So SN2 will not happen, but elimination will. But the best way to extract proton will be in a carbon that it's not hindered, right? Is not a lot of carbons or other compound or other atoms around. But we have this one over here as well, because the bromine will leave and we will extract the carbons and the place in the beta carbons, right? This is the beta and this is beta. So here we can extract this, but it's hard because we have, it's a buck base, and of course it will happen, but it's very slow because it's hard to get there because the sterically buck base. So, but we can also extract this. Now here we'll leave behind the electrons over here, and here what we leave behind over here. So again, we're gonna have a two product. There's one and there's one. But since we have a buck base, and the easiest way to extract a proton is in at least substitute the carbon, this is Hoffman and is our favor here. Okay? So remember that U1 mechanism will favor site product and cannot change this regioselectivity even if sterically hindered alcohol is used as a weak base. And also E1 reactions can undergo a rearrangement. So when the chlorine leaves here, we're going to have a carbocation and a secondary carbon. Last class, we talked about hydride shifting. So in order to have a more stable carbocation, it would be great if this positive charge would be located in the tertiary carbon. Remember about the neighbors, when we have more neighbors and more stable, we have more friends around to help us. And how that happens. So we have hydrogen over here that will move its electron to this position over here, and this charge will be moved to the tertiary carbon, exactly how you did the resonance. Remember that when you move the double bonds, the charge also move it of the electrons, right? So it's a movement of electrons. So now I have my charge over here, and what's gonna happen when we extract it? We can extract a proton over here, or we could extract this is the alpha carbon, we could extract over here as well. So when the base come here and extract the proton, this proton will leave behind the electrons forming the double bonds, and we're gonna have here a tetra substituted, and this is Zaitsev, right? So just remember, if you wanna produce some Hoffman, the only way is using E2, choosing a spherical base. If you produce, if you don't have a spherical base, you're gonna produce Zaitsev. So here you have sterically hindered base is this one. Okay. Okay, that's it. That's all.